Okay, so I wanted to go over some of these problems on time value of money and annuities on the worksheet. This first video is going to go over the time value of money problems, and another one will go over the annuities questions. So these are the questions on time value of money. So I'll come up here and have the question, and then we'll go over the solutions I wrote up. So number one, find the future value of $30,000 invested at 4 3/4% annual interest rate compounded quarterly for 10 years. So this is a pretty straightforward problem using the future value in terms of the present value and the interest rate. So the F equals 1 plus I to the N times P. Just be sure that since we're compounding quarterly, you divide by 4 here to get the 0.011875 is the I, and N then is 4 times 10 is 40. And it works out to be 48,105.63 cents. Okay, number two. How much money must be invested at this moment to achieve a future value of $85,000 in 5 years if annual interest of 7.2% is compounded quarterly? So this is same formula, just going the other direction. So instead of being given the present value and getting the future value, you're given the future value and you have to find the present value. So let's look at how we would do that. Okay, future value of 85,000 in 5 years, 7.2% compounded quarterly. Since it's quarterly, again divide by 4 to get I is 0.018, N is 20, 4 times 5. And the only difference between this one and the previous one here, notice that instead of solving for F, we have F is 85,000 and we're solving for P. So that means we're going to have to divide through by this 1.018 to the 20th, or I hit it with a 1.018 to the minus 20th. Works out to 59,492.66. Remember that as you go forward in time, the monetary value is going to increase. As you go backward in time, it should decrease. So the present value here should be less than the future value. If you get a present value that's greater, you made a mistake somewhere. Same thing on number one. Started with $30,000. If you get a future value that's less than 30, you did something wrong there. You should get a future value that's greater. Okay, number three. There we go. Find the nominal annual interest rate that will yield an effective annual rate of 8.125% if interest is compounded weekly. So this is going to use the formula that relates the nominal and the effective interest rate. So let's just review what that is. So the original formula that I'd given before was the effective rate is 1 plus I to the M minus 1. Here, there it is right there. I actually wrote it out here as R nom over M, so the nominal rate divided by M, because that really, instead of putting it in terms of this I that you have to figure from the nominal rate, it really is a formula that directly relates the nominal and effective rate. Now you have to figure out what M is here, but that's just the number of compounding periods per year. So if you know that, then this is a formula that directly relates these two. So we have M as 52 here because we're compounding weekly, and we are given an effective rate of 0.08125. So that's that. So plug that in. It's 1 plus I to the M minus 1. Go away, Avast. Okay. And so we get that if you add 1 to here, 1.08125 equals 1 plus I to the 52. And since we're solving for I, the only way we can get rid of the 52 power is to raise everything to the 1 over 52. Or, if you want to think of it in terms of radicals, you're taking the 52nd root. So 1 plus I is 1.08125 to the 1/52nd power. And then subtract 1 from that. And if you enter this into the calculator, raise it to the 1 over 52, and if you have the calculators, you can do parentheses, just go caret, left parentheses, 1 divided by 52, right parentheses. Don't try and convert this to a decimal and then plug it in. It's better just to do it as an exact fraction. You're going to get a more accurate answer. So we get this, and now I would kind of copy this down here. 1.00150339, and you take away the 1, this is what's left over. Now this is the interest rate for week. This is just per week. So that's the nominal rate per week, so we have to multiply that by the number of weeks in a year, M, 52, to get the nominal rate per year. So you remember this relation between this I. I is defined as the nominal rate divided by M. So the nominal rate is I times M. So always remember to convert it back to the yearly rate. It's usually not going to be in the yearly rate. So that becomes 7.82%. So 7.82% nominal, when you compound it weekly, gives you 8.125% effective. Number 4. Which investment is more attractive, one that pays 9.75% compounded quarterly or another that pays 9.7% compounded monthly, and why? Okay, so let's look at how we would compare these two. On all these kinds of problems where they're asking you to compare to interest rates, they're usually going to be different, compounded over different number of times per year. So the only way to really compare them then is to compare the effective rates. You can't just look at 9.75 and say, well, that's bigger than 9.7, so it must be better. If it's compounded, if the 9.7 is compounded monthly, that's more often, so that might make up for the fact that it's a slightly lower rate. So let's compare the two, remembering that to find the effective rate, it's 1 plus r over m to the m minus 1. So for the 9.75, if you take a quarter of that, add 1, raise it to the 4th, subtract 1, we get an effective rate of 10.11%. If you do the same thing to the 9.7 here, divide by 12, add 1 to the 12th, minus 1's 10.14, just a little bit bigger. So in fact, the 9.7, if you compound it monthly, is a higher effective rate than the 9.75 compounded quarterly. So it's better to invest at 9.7% compounded monthly. Number 5. How much time is required for an investment to double in value if interest is earned at an annual rate of 6% compounded monthly? Round up to the nearest month. So the reason I said to round up is if you rounded down, you really wouldn't have doubled it. You would have almost doubled it. So you have to do that extra month to complete the doubling amount. Okay, so how can we think about this? How much time to double? First of all, one thing you might have noticed, I didn't say how much the principal was. Principal is not given. Well, why is that? Well, let's see what happens if we think of a principal amount. Just call it P. Use our formulas, original principal amount. Now, what we're trying to do is find the future value to be equal to 2 times the principal amount. Right? We want to have the future value be twice the original amount. That's what it means for it to double. But the future value is 1 plus I to the n times P. So we should be able to set this equal to 2p. And when you do that, aha, there's a P on both sides. So you can cancel those out. So what that means is that solving this problem of doubling time really doesn't have anything to do with the principal. You could be investing $1,000, you could be investing $1, you could be investing $1 million. It doesn't matter. The doubling time is the same. So our I here, R over M, is 0.06 over 12, so 0.5%. That's the monthly nominal rate. And we want to see how many times do we have to multiply that by itself. So raised to the n equals 2. And this is one of those problems that I said if you're solving for an exponent, you have to use these log functions on the calculator. It's always the log of the one side of the equation without the variable divided by the log of the base. So in this case, log of 2 divided by the log of the base, 1.005. And it gives us 138.98. So we're going to round that up to 139. So 139 months works out to 11 years, 7 months to double the principal at that interest rate. Okay, number 6, last one. This is a, let's see. Okay, Rachel has $80,000 she wishes to put in a savings account. If interest is compounded daily, which is for all practical purposes, you can treat it to be continuous, but let's say daily. She wishes to earn at least $2,000 in interest by the end of the year. What's the minimum nominal stated annual interest rate she should accept? Yeah, I found it kind of weird to write these problems because it's really strange because the interest rates are so low now that some of these problems really don't seem very realistic at the moment, although they did at some point in time. But when you have really low interest rates, it makes it really hard to construct a good math problem because interest rate of 0.5% or 1%, the numbers just don't illustrate the idea very well as if you have a higher interest rate. So 9.75%. Good luck now, but anyway, let's just go ahead and see what interest rate we would need here. So okay, so the main thing to look at this one is you have to realize that if you want the $2,000 interest, you have to think about that as the $82,000 is the future value. So we're looking at solving future value equal to that. So we set up our equation relating f and p. Here, m is 365, so I is r over 365. Okay. And p, the present value, is 80,000. So 80,000 is growing to 82,000. So plug those in. 82,000 is 1 plus I to the 365 power times 80,000, which means 1 plus I to the 365 has to be 1.025. And this is very similar to how we were solving I before in the previous problem. You raise both sides to the 1 over 365 power, subtract 1, get this very small number close to 0.00006765328. Actually, on my calculator when I did it, I got said 6.76, and it had the scientific notation e to the minus whatever this is, 1, 2, 3, 4, 5. So you need to understand how to recognize this scientific notation if your calculator does that. Then remember, you have to multiply by 365. This is the daily rate. So go ahead and multiply that by 365, and it's 2.47%, which is, you should have guessed somewhere around 2.5%, because 2,000 is 2.5% of 80,000. But you need a slightly less nominal rate. I wish I could do a realistically higher interest rate. You'd see that this could be a little bit less than what it is here, but anyway. So the next video we'll go over the annuities worksheets. annuities problems.